Screens. All right, welcome everybody. It's time to start. Today, Mateo Muro from CU Boulder will talk about a characterization of finitely based abelian multivarieties. Please, Mateo.
Thank you, Peter, and thank you to all the organizers in PAL for having me. Today, I will be talking about the characterization of finitely based abelian multivarieties. This is based on a paper I have submitted to the archive, which you can find. I'll be introducing the basic notions and then talking about, I'll state the main results and of course, give an overview of the proof and talk about some future directions, some new stuff I want to develop for the future. Right, so first I have to talk about the finite basis problem, a little bit of the history, really define all the notions and necessary. Then, like I said, we'll talk about abelian multivarieties, a few more notions, and this is where I talk about my research and my work that I've done. And then again, like I said, future directions. So starting with the finite basis problem, I want to get some preliminary stuff out of the way. Some of you may be familiar, but for those of you who aren't, an algebra, in simplest terms, is a set with operations. And this is best illustrated with an example. So it's usually written as a tuple like this. Here we have the algebra that is the group structure on the integers. Your set is the integers. Your operations are going to be addition, negation, and zero. Here, addition is binary, negation I think of as unary, and zero I think of as nullary, basically a constant. And there's a few technical details about what constitutes an operation, but the simplest way to think about it is like this, a function from some power of the set to itself. If you don't like numbered examples, there's also algebras that are lattices, for example. You have your set, the lattice L, and you have two binary operations, meet and join. So a set of operations is going to need to be named, and we'll call it the signature. So in this first example with integers, our signature is addition, negation, and zero, for example. So a variety V is going to be a class of algebras with a fixed signature that are defined by a set of equations or identities. This set of equations, sigma, will be called the basis for the variety V. So for example, the variety of groups that has a fixed signature, addition, subtraction, zero, and it'll satisfy its basis will be the group axioms, which constitutes associativity, identity, and negation. All right, so these are what equations are going to be looking like. And these sets of equations defines the variety groups as we know it. Similarly, there's a set of equations that defines the variety of lattices, and there's also one for rings, etc. Varieties generated by algebra is an important notion. If A is an algebra, then I'm going to use V of A to denote the variety generated by A, and that will be, strictly speaking, the variety of algebras satisfying all the equations that are true in your algebra A. Equivalently, I can also take the class of homomorphic images of subalgebras of direct powers of A. These two definitions are equivalent. That's a non-trivial fact. So for example, if we take our group of integers, the variety that will generate will be the variety of abelian groups. You take all the equations that are true in your group of integers, and those equations will be satisfied by abelian groups. Similarly, if I take any homomorphic image of any subalgebra of any direct power of A, what I'll end up with is an abelian group, and I'll be able to get any abelian group like this. Okay, so now I want to talk about what a finite basis is, what it means to be finitely based if you're a variety or algebra. This means, well, that your basis of equations is finite in size. So for example, the variety of groups, that's you think of them as 3 axioms, but I think it's technically 5. Point is, it's a finite size. Lattices, also a finite size. I don't know the number off the top of my head, but finite in size, so we say the variety of lattices is finitely based. In algebra, will be finitely based if the variety it generates is finitely based. So for example, the group of integers is finitely based because the variety it generates is the abelian groups, which is finitely based. So then the question becomes the overall question is which algebras and varieties are finitely based and which ones aren't. And in the 1960s, more specifically, it was asked for an algorithm by Tarski. So the question is there an algorithm that, given a finite algebra as input, will the algorithm be able to determine if there exists a finite basis or not? A finite algebra with finitely many operations of finite arity is definitely encodable into finite information. So it's definitely within reach, and it would be great to find out that there is such an algorithm for all such algebras. Of course, in 1996, Mackenzie provided a negative answer with quite a clever proof. Involves constructing for each Turing machine an algebra, which we call A of T, which would be finitely based if and only if your original Turing machine halted or not. So if you know a little bit about computability theory, you know the halting problem is undecidable. And so here, Mackenzie reduced the problem to the halting problem, which is undecidable. So that shows that there does not exist such an algorithm. So now we ask in the modern era that can we characterize any finitely based algebras in well-behaved classes? And we have a few results, for example. First, to kind of show that there are finite algebras that are not finitely based, Linden has an example from 1954. You might think that because an algebra is finite in size, its equational theory would be bounded somehow. We've known since 1954 that it is not true. But Oates and Powell showed just a decade later that at least every finite group is finitely based. And that took a lot of work, but it does go to show that groups are a very well-behaved class. And then almost 2 decades later, we have that every finite super nilpotent Maltsev algebra is finitely based. And that's sort of where I started my research. I wanted to know what Maltsev algebras were, what nilpotents and super nilpotents meant. That leads me to my next section on abelian Maltsev algebras. So I have to define what Maltsev algebras are, or a Maltsev variety rather. A variety V is going to be Maltsev if there exists what I'll call a Maltsev term M of XYZ, such that V satisfies this equation M of XXY equals Y equals M of YXX. It's ternary. By term operation, I just mean that from your signature of basic operations, you can somehow get this Maltsev term from composition. For an easy example, take any additive group or any expansion of additive groups such as rings or modules, you have the very easy multiplicative term m of xyz equals x minus y plus z. And so you can quickly check that m of yyz is, for example, y minus y plus z, which is z. And these are well studied because underneath the hood, you can see that they have well-behaved congruences. Abelian algebras an algebra is going to be abelian if the commutator of your total congruence with itself yields the trivial congruence. A variety is going to be abelian if it consists only of abelian algebras. So I haven't defined what a commutator is, and that's a whole chapter worth of defining. But thankfully for this talk, you just really need to know this result, which, as I could tell, I can attribute to Goom in 1980. Not said exactly like this, but very close. A variety with multiplicative term m is abelian if and only if for every basic operation f, we have this equation, which basically says that m commutes with f. First thing you should notice is that m and f switch order in the equation. So I could read it as m of f of x1 through xk, that's what the x bar means, f of y1 through yk, and f of z1 through zk is equal to f of m x1, y1, z1 through m of xk, yk, zk. So yeah, I call this m commuting with f. And yeah, like I said, you want m and f to sort of switch places for them to commute. And you count up variables. This is sort of the only way it can work if you want two operations to commute. Right. So really for abelian multiplicative varieties, this is how I think about it, is satisfying this condition with the multiplicative term rather than thinking about commutators and such. For example, you take this exotic algebra, your set is the integers, your first operation is the multiplicative operation, x minus y plus z. And then you can take, as your third operation here, I chose 3x plus 4y plus 3. You have your multiplicative term right there. And so you just have to check that these two commute. And once you have verified that they commute, you know that this is an abelian algebra. So free algebras are also important. For variety v in variables x1 through xn, I'm going to let fv of x1 through xn denote the free algebra over x1 through xn. The free algebra, you want to think of it as taking your generators x1 through xn and sort of iterating your basic operations over and over. A term T is idempotent in a variety V if V satisfies that T of all Z's is Z. That's for terms. Here, I'll let FV ID x1 through xn denote the idempotent elements of a free algebra, x1 through xn. So technical detail is that sometimes I'll think of the free algebra as being consisted of terms. It's not technically correct. It's the terms over an equivalence relation. If you don't know what I'm talking about, it's not important. It's very easy to think about these as in terms of terms. So in spirit, Ralph Rees and Ralph Mackenzie in 1987 showed this module structure, which I'll name in a second, but first I have to give you the operations. For a given abelian variety V with mults of term M. I want for any S and T in the free algebra on two generators to be able to define this addition, multiplication, and negation. So S plus T, I want to be M of S comma Z comma T. Multiplication, I want to define using composition. So it would be S of T of X, Z, Z. And negation, I just want to be M, Z, S, Z. And so what we get is a ring structure first on the idempotent binaries, or the idempotent elements of the free algebra in XZ. Addition, negation, multiplication being defined like this. Your identity will be X, your zero is Z. It's pretty rote to just check that addition is commutative, multiplication distributes. Even just checking that you're closed, you're going to end up with another idempotent element if you add or multiply like this. And you also get an RV module. So having this ring RV, you can get this RV module on the free algebra on one generator. Same addition, same negation. I think of RV as being a set of unary operations. This is the scalar multiplication. And your zero is going to be C. Again, very rote to just check that addition is commutative and scalar multiplication distributes and all those axioms. So interestingly, you get that the free algebra on XZ with addition, subtraction, and RV as your scalars, you get that it's isomorphic to RV and MV as RV modules. Here, RV acts on itself in the usual way that a ring is a module on itself. And so what I was wondering was if somehow this ring is related to the equational theory. If the ring or module is finitely presented, does this mean that the equational theory is necessarily finitely based? Well, I came up with this results, which again is on the archive as of December, I think. If you have an abelian mults of variety V, your V will be finitely based if and only if you have a finite signature, most importantly. But then that your ring is finitely presented as a ring, and your module is finitely presented as a module. So I would give examples, but they're all pretty involved. The easiest example is to think of, easiest example is thinking of modules over a given ring R. Your RV ends up being R. So if you want a non-example, you have to think of R modules for a given non-finitely presented ring R. Also, that finite signature is just there. If you're finitely based, you're only talking about finitely many operations in your basis. And if you have an infinite signature, you have no chance of having a finite basis. So that's my main results. If there are any questions, of course, feel free to interrupt. But otherwise, I think I have time to go over most of the proof. The first thing is that we want to translate our variety V to something maybe not simpler, but more tangible. So if you have an abelian mults of variety V with mults of term M, then I can consider the equivalent variety W, where the operations are coming from FV of Z, FVID of XZ, and M. If V has finite signature, then I just pick finitely many from each of these sets. So I can call them U1 through UL for the unary terms, R1 through Rn for the binary terms, and of course just M for the multiple term. So equivalent variety just means something very technical, but I think of it as you're able to recover. Well, first off, they have the same algebras. They're the same class of algebras. They have different signatures, but you're still able to express the same terms. So if you're able to describe all the terms of V and W and vice versa, you're basically equivalent, is how at least I think about it. Okay. The way this works is that V decomposes into a sum of unary and binary terms. And this kind of follows from the binary terms already splitting into unary and idempotent binary terms. But here I give an example of what happens with a ternary term, f of x1, x2, and z. You can see that you replace each variable with an equivalent multiplicative term, and then you use that M and F commute. From there, I know addition is used in terms of multiplicative term and works out to be this way. And so what I have is my first idempotent binary term is this f of x1 zz minus f of z zz. If I make that all z's, I get 0, essentially. So that's idempotent x1z. Similarly for f of z x2z minus f of z zz. And finally, the last one is just a unary term. So yeah, I gave you this example for ternaries as sort of the basic example, and it inducts easily conceptually, but it gets very messy if you want to write it out, for example. So for example, we go back to our exotic algebra with the multiplicative term and 3x plus 6y plus 3. This will be equivalent to an abelian variety in the signature. Still your multiplicative term, x minus y plus z. But now we have idempotent binary terms, 3x minus 3z, 6y minus 6z, and then we have the unary 9z plus 3. And notice that this isn't necessarily simpler than my first algebra. But now I'm working with W, it doesn't matter. The point is that any abelian multivariety can be reduced like this to some set of finitely many binaries and unaries to work with. And so, of course, that I mentioned is equivalent varieties. Something that's a variance under equivalent varieties is being finitely based. So now my goal is to prove that W is finitely based. To do that, I need to define a larger auxiliary variety U with the same signature. It's going to have U1 through UL, R1 through Rn, and M. It's going to satisfy the following axioms. M is multiv. The Ri's are idempotent. And M commutes with every basic operation. What I get if I define U this way is a list of helpful properties. First of all, U is finitely based. I use only finitely many equations to define it, so it has to be finitely based. Secondly, it's going to be the largest abelian multivariety in this signature. That'll be important. Most importantly is that the ring Ru is going to be free over these Ri's. And also the Ru module Mu is going to be free over these UIs. That'll be important, mostly because the variety of W is a subvariety of U. What's going to end up happening is that this works out so that RW and MW are going to be quotients of these rings and modules, which are free. So that takes work. And so the first thing you have to consider is this morphism from your free algebra U. That's going to be over countably many generators, FU of X1 forever, to FV, that should say FW X1, and so on. It's a typo. And you just want to take your terms from U and project them into your free algebra in W. There's sort of no good notation for this. But because U is sort of this freer variety, you know that the kernel might not be trivial. It may be that two terms get mapped to the same place in the free algebra in W, because W may satisfy more relations. By Birkhoff's theorem, we know that W is going to be finitely based relative to U, if only if this kernel of this morphism is going to be finitely generated as a fully invariant congruence of FU of X1 forever. And so finitely based relative, this means that W is definitely contained in U. You need only finitely many equations to define W inside of U. But of course, U is already finitely based, so it's just saying W will be finitely based if and only if this kernel is finitely generated. One of the most important lemmas in my paper is first showing that every fully invariant congruence in this free algebra U, X1, so on, uniquely determines a pair of ideals in RU and a submodule of MU. Meaning there's sort of this map from every fully invariant congruence to an ideal and submodule. Conversely, I can take any pair of ideal of RU and any submodule of MU to determine a fully invariant congruence of FU of X1. And of course, some of you will recognize that ideals and submodules will correspond to congruences in ring theory and in module theory. This correspondence is especially important because the finitely generated fully invariant congruences of FU are going to be in bijection with the finitely generated ideals and submodules. So given any finitely generated fully invariant congruence, I can find a finitely generated ideal and submodule and vice versa. There is a tiny compatibility relation if you happen to be one of the two people who have read this paper already. But for the most part, it's a nice, well-behaving correspondence. All right, so now I have all the parts to prove that W is finitely based if and only if the ring and module are finitely presented. And pieces are like this. You want to start with the morphism that I mentioned, FU from X on countably many variables and FW on countably many variables, where the terms are just projected, and just let theta be your kernel. So if W is finitely based, then theta is going to be finitely generated as a fully invariant congruence of FU. This is due to Birkhoff's theorem again. And so that means theta is going to uniquely determine a finitely generated ideal I of RU and a finitely generated submodule N of MU. Once I have those, I already have that, part of the proof involves showing this is true, but it is true that RW is isomorphic to RU mod I, and MW is isomorphic to MU mod N. Since RU and MU are free with finitely many generators, the RIs and the UIs, which there were N or L many of, that means RW and MW are finitely presented, and that proves the forward direction. Backwards direction is similar. If you start with finitely presented ring and finitely presented module, I'm going to get that there exists some ideal I and some submodule N that this is true for. RW and MW are definitely quotients of RU and MU. If it's finitely presented, this I and N are both finitely generated. And this correspondence goes in the other direction. I'll be able to find a finitely generated fully invariant congruence theta. And I'll be able to translate that into a finite basis. Okay, so now I want to talk about future directions for a little bit. The main obstacles. So the first main obstacle, well, I should have given this a slide, but this was a characterization for abelian Maltsev varieties. Abelian varieties are obviously a generalization of abelian groups using commutators. We can also generalize nilpotent groups to come up with nilpotent varieties and nilpotent groups. And so now my goal, my dream is to come up with the characterization for finitely based nilpotent Maltsev algebras and varieties. So given a Maltsev variety of finite type, can I find a subvariety? Well, can I find a basis for the subvariety Vn of n nilpotent varieties, algebras in V? So I gave a basis for due to GUM in the case that n is equal to 1. That's abelian algebras. That was easy. That was just saying that the Maltsev term commutes with every basic operation. So with finite signature, that's easily a finite basis. I know that commutator theory, you can find a finite basis if your free algebra on XZ is finite. So they give a general, Friesen-Mackenzie give a basis for n nilpotent algebras that's not necessarily infinite unless you assume your free algebra on two generators is finite. It's for very well-behaved varieties. In general, you think of even just the free group on two generators, that is definitely not finite. So that's sort of my first big obstacle, is trying to get everything in terms of just to break it down into, to find a subvariety, a basis for a subvariety of n nilpotent algebras isn't as easy as just saying M commutes with this many operations. Now it has to be M almost commutes and also a lot of other things. There's a lot more details in commutator theory for congruence modular varieties. And then the other problem is the non-abelian group structure. So part of the paper was defining addition, multiplication, and negation so that you can recover this ring and module structure. And it's not true. You're not going to get a ring on n nilpotent algebras. I forget what addition gets you, but it's definitely, so far all I've got is that loop multiplication on any free algebra in a nilpotent variety, defines a loop. It might be that addition gets you nilpotent groups, but then, like I said, you're not going to get ring structures. You're not going to get module structure. I conjecture you're going to get some sort of exotic algebra, something that's not named. at the very least. And maybe there is no compatibility between multiplication and addition. But still, it'd be nice to find out that I can still translate equational theory of a general abelian nilpotent variety to the equational theory of maybe a simpler algebra or something more normalized. So yeah, those are my current obstacles. If you're interested, you can find this again on the archive. My name is Muro, and that was put up there only a few months ago. It's got a very similar title to this talk, Characterizing Finitely Based Abelian Multiple Algebras. And I'd be happy to talk that over with anybody. Thank you.